Okay, let's go ahead and get started. So, we've more or less finished our discussion of special relativity in this class, and now we're going to move on to some slightly more advanced topics. So this week will be spent studying the general theory of relativity. We won't go into all of the mathematical details of the general theory of relativity because I don't want to say that it's beyond what you could understand at this point, because it's certainly not. But it's certainly a bit more detailed than the mathematics behind general relativity is more detailed and would require a substantive background that I really don't want to spend this course developing. I mean, there's a whole course on general relativity that one could take if one were interested. So I am basically going to spend roughly a week, maybe a little more than a week, going through some of the basic notions of general relativity. I'll describe those effects of general relativity, which can be understood as a straightforward extension of those in special relativity, without diving into any of the mathematical details. And this will lead into, after the midterm, starting later next week, a very basic discussion of cosmology. I'll describe to you a few of the general features of the structure of our universe at its largest scales, and how we describe them using the language of general relativity, and what the observational implications of this description of the universe is. Okay. But before doing so, before I even get into the subject of general relativity, I just want to say a few words maybe to set the stage and to bring some of the concepts that we'll be discussing into a language that is a bit more familiar to you. I want to say a few words about the unification of electricity and magnetism. Because it turns out that the mathematics of general relativity is, in fact, in many ways, very, very similar to the mathematical description of the electromagnetic force in special relativity. And as I've alluded to a few times earlier in this course, in fact, electricity and magnetism play a special role in the history of special relativity. And indeed, when one thinks about electricity and magnetism in the context of special relativity, we see the first example of something which is of a phenomenon which has been ubiquitous in physics over the last century, namely that of the unification of forces. Okay. So what do I mean when I say unification? So when we say that two concepts in physics are unified, what we really mean are that two previously distinct physical ideas or physical phenomena, if I can spell phenomena right, are realized as different manifestations of a single more fundamental or more basic phenomenon, which I still can't spell. So, for example, we have seen that the notions of space and time in special relativity do not individually have an observer-independent meaning. Indeed, the only thing which has an observer-independent meaning is the invariant interval, rather than a time or spatial separation. And so we regard space and time in special relativity not as distinct concepts, but rather as part of one more unified concept, which we refer to as space-time. Likewise, momentum and energy are completely distinct quantities in Newtonian physics, that a priori have little to do with one another. But one of the things that we have discovered is that, in fact, what you call energy and momentum is a frame, that is to say, observer-dependent statement, and that these are really just different manifestations of a single, more fundamental quantity, which is the energy-momentum 4 vector that we discussed over the last week or two in this class. So these are two examples of unification in physics. And what I'd like to spend at least a few minutes talking about at the beginning of class today is another sort of unification. And this will be a unification of forces. So what we will see that two a priori unrelated forces, namely that of electricity, or the electric force and the magnetic force, are in fact two different manifestations of a single, more fundamental force, which we usually refer to as, well, not very creatively, the electromagnetic force. So, in order to understand why electricity and magnetism must, in fact, be two different manifestations of a single, more fundamental concept, let me remind you that one of the most basic principles of relativity, and indeed of physics, is that the outcome of some experiment should be independent of the variables that one uses to describe the experiment. So, for example, if I wish to describe the outcome of some experiment and I use coordinates in one reference frame that might be at rest with respect to our laboratory, then the outcome of the experiment shouldn't depend on whether I use that reference frame or another reference frame that is moving at some constant relative velocity. And so what I would like to do is I would like to think about a very particular experiment that we could perform in some laboratory and use that to argue to you that necessarily electricity and magnetism must be unified in some way. So let's consider the following. Let's consider a current which is moving through a wire. So here I have some wire. So I'll draw the wire with some thickness so that we can think about the dynamics of what's going on inside the wire. And let's say that I have some electric current, which is usually denoted by the symbol I. Okay. So what does it mean that I have an electric current? Well, microscopically, there are lots of charged particles in this wire. Namely, there are electrons which have a negative electric current, and there are also protons which have some positive electric charge. And the statement that we have a current is a statement that these various charged particles inside the wire are moving. And so if I have, as I have drawn here, a current that is moving to the right, that means that all of the charged particles inside this wire are moving to the right with some velocity, and all of the negatively charged particles are moving to the left with some velocity. Okay. So the positively charged particles are moving to the right with some velocity, and the negatively charged particles are moving to the left at some velocity. And although these particles are moving, and there are charged particles present, the wire is overall electrically neutral, in that, for example, the density of positively charged particles is equal to the density of negatively charged particles. Okay. And the current arises because we have some flux of positively charged particles moving to the right and negatively charged particles to the left. So let's now consider the following experiment. Let's take some charged particle. It could be another electron, or it could be some other charged particle like a proton that is positioned outside of the particle, outside of the wire, and is moving with some velocity v. Okay. And then we would like to ask, what is the motion of this charged particle? And let's first analyze this in the frame of the lab, where the wire is electrically neutral and the particle is moving with some velocity v. So in that frame, the current will lead to a magnetic field, usually denoted B, which we won't bother to work out the details, but roughly speaking, if here's your wire with a current in that direction, then there'll be some B field which is in a circular direction that surrounds the wire. So is that familiar to you? Hopefully this is familiar to you. This is, I guess, Ampere's law or something like that. It says that if you have a current, then you'll have some circular B field moving around it. And so if you have your charged particle here moving with some velocity v, then the charged particle will feel a force which is given by the Lorentz force law, which is Q over C times V cross B. Okay. And in order to determine the direction of the force, we just use the right-hand rule. So V cross B, if V is moving to the left, so that charged particle is moving to the left, and B is pointing out away from the blackboard at the point of the charged particle, then V cross B is up. So the force on the particle will be a force in the y direction whose size is Q over C times V times the strength of the magnetic field. Okay. So all of this is perfectly straightforward. It's the sort of problem that you would have considered in your freshman electricity and magnetism course. Yes?
What is C?
What is... Sorry, what is what?
What is
C.
C?
C is the speed of light. Are you familiar with this expression for the Lorentz force law? Okay. Are you familiar with the statement that the force is V cross B? Okay. The force is V cross B, and there's an overall constant outside of the force. So you may have seen it as written as the product of mu times epsilon. You've seen that? Okay. Which is, in fact, the square of the speed of light. I don't want to dwell on the normalization of this force, but I just want to remind you that you are hopefully familiar with the fact that if you have a current flowing through a wire and a particle that is moving in the presence of that wire, then it will feel a force due to the magnetic field created by that wire. That force will be in the y direction. Is that statement acceptable to everyone? Good. Now, so in particular, this particle is going to move away from the wire. Okay. Now, let's consider the analysis of this experiment in a different frame. Let's consider the analysis of this experiment in the frame moving along at velocity v in the x direction. Okay. In particular, in this frame, so I'll take velocity v moving to the left. So in this frame, the particle is at rest. And so, if the particle is at rest, it will feel no magnetic force. Now, at first sight, this appears to be a disaster. Because remember, one of the basic principles of physics, the basic principle of relativity, is that the outcome of an experiment shouldn't depend on which variables you use to analyze the setup. It shouldn't depend on whether I decide to use a frame where the velocity of the particle is equal to 0, or I decide to use a frame where the velocity of the particle is equal to v. Question?
The particle we're talking about inside or outside?
The particle is the particle with charge q, which is right here. Okay. So it's got some velocity v. So in this frame, the particle's not moving. And so the magnetic force, V cross B, is equal to 0. And in particular, V cross B is equal to 0. Okay. So what we conclude then is that in this frame, the particle must still feel some sort of force. But it can't be a magnetic force, because V is equal to 0, so a particle will never feel a magnetic force. And so what must happen is that the particle must feel an electric force. So in this frame, there must be an electric field. Question? Yes? F is the Lorentz force. Okay. If you have usually in the Lorentz force law you have Q times phi, okay? Or you have an electric field, so you have Q times E. But for a current moving through a wire, there's no electric field. There's only a magnetic field. So I didn't bother to write that part of the equation. Now, however, in the frame where the particle is at rest, where V is equal to 0, my claim is that there must now be an electric field. Okay. And why should that be the case? Well, let's consider again our microscopic model of our wire. So we had some negatively charged particles moving to the left and some positively charged particles moving to the right. And these particles will be moving at some typical velocity. So the typical velocity of one of the negatively charged particles I'll call V minus. And the typical velocity of one of these positively charged particles I'll call V plus. And the contribution to the current of some moving density of charged particles is the density of the charged particles times the area of the wire times the velocity at which they're moving. So, for example, the total current will be the density of the plus charges times the velocity of the plus charges times the area minus the density of the minus charges, because they have negative charge, times the area times the velocity of the minus charges. And in the frame where the wire is at rest, then the statement that the wire is electrically neutral is that rho plus is equal to rho minus. So in the frame where the wire is at rest, rho plus is equal to rho minus, and the wire is electrically neutral. It has no net electric charge. But in the frame where it is moving, what is going to happen? Well, the first thing that you notice is that you'll have to take into account length contraction. And so if, for example, the object that we're considering, this charged particle, is moving to the left, then the plus particles will be length contracted more than the minus particles. And so, in particular, rho plus is increased in this frame, whereas rho minus is decreased. So, for example, you could imagine the case where V is equal to V minus, so that in the frame where the particle Q is at rest, the electrons, the negatively charged particles, are also at rest. And then rho minus, you can see that rho minus will definitely be decreased because the horizontal direction won't be length contracted at all. But rho plus will be increased because the frame of the charged particles will be length contracted. And likewise, the velocities v plus and v minus will also change. So v plus and v minus will also change due to the velocity addition. With the net result that the wire is no longer electrically neutral. So in this frame where the particle is at rest, but the wire is moving, there will be some sort of electric field produced by the wire, which will push the charge Q vertically away from the wire. So that at sub y, the force in the y direction, the vertical direction, is still non-zero in this frame. Question?
Could you just have said, since the current's moving, there's magnetic field that is induced, and having a moving magnetic field according to the induced frame induced magnetic field? Since
You could, I guess you could, but well, I guess you could say it that way, yeah. Yeah, time-dependent magnetic field produces an electric field. Yes?
I'm not sure if my question asks the same thing, but Maxwell presumably figured all this out without the help of special relativity.
That's correct.
It hasn't really been invented yet.
Yes.
So he must have done it, or must have come up with these same relationships between electric and magnetic fields in some other way.
Well, it's actually an interesting piece of history. Maxwell actually didn't do it. It was Lorentz, who first discovered the way that you have to modify the transformations between space and time in order for Maxwell's equations to be invariant. Okay. There's a reason why we call them the Lorentz transformations and not the Einstein transformations, which is that Lorentz actually was after Maxwell by some decades, but before Einstein for some decades. Okay. I think the reason why Einstein is famous and Lorentz is somewhat less so, is that Lorentz didn't really understand the physical implications of these transformations. And the physical implication is literally that in order to preserve the principle of relativity, namely that the observed effects, say the motion of this particle in the y direction, are independent of what coordinates you choose to parameterize the system, we see that electricity, the electric and magnetic forces, are really different manifestations of the same thing. So whether you call something an electric force or a magnetic force is dependent on what frame you're using to describe the setup. So in particular, these forces mix under a Lorentz transformation, just as space and time mix under Lorentz transformations. So whether you call a particular force due to an electric field or a magnetic field is dependent on what your reference frame is, what reference frame you're using. Yes?
For this question, so the number of protons and number of electrons should be
That's great. The number of protons and the number of electrons is the same, of course. That's not going to change depending on what frame you're in. But the density of electrons, which is the number per unit length, and the density of protons, the number per unit length, will change because of length contraction. No, the wire is not neutral in a frame where it is moving.
Why? Number of protons.
But when we say density, we mean the number at a given. Okay, I mean it's a little subtle.
Is this multiple expansion?
No, this is not a multipole expansion.
So first you have
Yeah.
one proton from dipole.
Yeah, this is not a multipole expansion. It's just the statement that, for example, V plus and V minus will change due to the velocity addition formulas, and lengths will be contracted or dilated according to these formulas. Let me say it slightly differently. Let's imagine that instead of a single wire, we had two wires, one with positive electric charges and one with negative electric charges that were right next to each other. Okay. In the frame then I think that makes it a little clearer that in the frame where all of the electrons are at rest, the density in the electron wire will be different from the density in the proton wire. Now, you know that this has to be true. You know that something like this has to be true because otherwise there would be no way to get the same result independent of which frame you use to describe the physics.
But in this case, the number of protons won't change, but the length will change.
That's right.
So we don't have multiple dipole.
I guess I don't know quite what you mean by...
Because the number of protons is unchanged.
But the density is changing. So the multipole expansion is first of all, you shouldn't really talk about a multipole expansion for an infinite object. So I don't know quite. A multipole expansion is something that you can do for an object with finite size. But these are, in this approximation, infinite wires.
In this case, the dipole moment is not visible.
And so, there's no multipole expansion for an infinite wire. So I guess I'm not quite sure what you mean by that. A multipole expansion is something you do for a finite collection of charges that are static. Maybe I'm not understanding what you're trying to say, but one can't really use a multipole expansion to describe a collection of moving charges on an infinite wire. Yes?
Are we talking about a finite collection of charges, like individual?
Well, what we're really doing is we're talking about it. In this approximation, we're talking about an infinite wire. Eventually, of course, you have to connect it to terminals, a plus and a minus terminal, and figure out what's going on there. But in this very simple model, I'm considering an infinite wire. And I'm also considering moving charges. And you need to be a little more careful when you're talking about the multipole expansion of moving charges. Yes. But you know that this has to be right. Because otherwise, you know that the particle has to move, okay, in the y direction. You know that this particle Q has to move in the y direction. And it has to move even in the frame where the particle is at rest. And the magnetic force V cross B is always 0 if the velocity is 0. So just consistency with the rule, the basic principle of relativity tells you that there must be some electric force present, because a magnetic force does no work. It will never act on an object that doesn't already have its own velocity. So you know that there has to be an electric force present. So even though the wire appears electrically neutral in one frame, it's not going to appear electrically neutral in another frame. Question?
Okay, so I understand what is actually going on, but why does the density of negatively charged particles decrease? Because it seems like
Let's think. I mean, think about the example where you have two different wires, one carrying positively charged particles, one carrying negatively charged particles. And let's take the case where V is equal to V minus. Okay. Then in the frame where Q is at rest, the electrons are also at rest. So then if you consider going back to the frame where the particle Q is moving with some velocity V, that means that that minus wire had to be contracted by some amount. Okay. So if you look at the density rho minus in the frame where it's uncontracted, and you compare it to the frame where it's contracted, then it will have to have decreased. I mean, I'm using here a particular mechanical model of what's going on in a wire, which of course is a little imprecise, where I'm just talking about particles moving around. But I wouldn't have to use this mechanical model. I could have just declared for you that physics has to be independent of whatever variables I use to describe it. And so if I use this reference frame where Q is not moving, there has to be an electric force there. And how it arises in a particular mechanical model of what's going on inside a wire depends on the details of that model. But you know that it has to be there. There has to be an electric force that pushes this, and in particular the wire has to have a positive electric charge because it has to push the charge Q away from the wire. Question?
Is it near or wrong, but I don't see why the density can be like 100 photons different, but the velocity will be different.
The velocities certainly are different.
So
Yeah.
the velocity is different, even if it's the same
Yeah.
density.
Right. I mean, even if you had the same densities, then you would still have different velocities because of the velocity addition formula. Yeah. Okay. So, what we have seen then is that there's no separate notion of electric and magnetic forces. That whether you say that the motion of an object is due to an electric force or a magnetic force is a frame-dependent statement. In the same way that whether or not two events happen simultaneously or one before the other or one after the other is a frame-dependent statement. One of the interesting features of electricity and magnetism, in fact, which is different from the transformations that we have seen earlier in this class, is that the way that E and B mix under a Lorentz boost is more complicated. Than the rules that we have seen earlier, for example, describing the way that T and X mix under a Lorentz transformation. So, in particular, let me just write down, without any proof or justification, the rule for how these quantities transform as one changes reference frames. So let's say that you have an electric field and a magnetic field that takes some values in a particular reference frame. And I'll choose some velocity vector v and go to the frame that is moving with velocity v with respect to our original frame. And I'll write E parallel and E perpendicular for the components of the electric field parallel to V and the components perpendicular to V, and likewise for B parallel and B perp, then the formula for the electric field in the new primed frame that is moving is given by something that is slightly different from the Lorentz transformation rules that we have seen so far. So the components of the electric and magnetic field parallel to the direction of motion are unchanged, but the components of the electric and magnetic field perpendicular to the direction of motion will change. And I don't want you to try and memorize or think too hard about these transformation rules, but I just want you to notice that the formulas for E perp and B perp, the second and the fourth formulas that I have written down here, look very similar in character to the Lorentz transformation rules that we've seen so far in this course. So remember that x prime is equal to gamma times x plus vt, and t prime is equal to gamma times t plus vx over c squared. Here you can see that there's a very similar sort of mathematical structure where E is going to gamma E plus V times B, and B is going to gamma B plus V times E. With the added complication that we're now dealing with vectors here, so we had to divide into parallel and perpendicular components, and I had to include some funny-looking cross product. And I just want to say one more word about this Lorentz transformation rule, that this is not the transformation rule for a 4-vector, such as that 4-dimensional vector containing t, x1, x2, and x3 under a Lorentz proof. But instead, this is the transformation rule for what is known as a tensor. And in particular, this is what is known as the transformation law for an antisymmetric 2-tensor. That's some fancy mathematical word that you don't necessarily need to pay too much attention to. But the point is that the world is a much more mysterious and complicated place than just the world of 4 vectors. Even if one is considering electromagnetism, the implications of special relativity are actually rather non-trivial. And what we have seen in particular is that 2 a priori very different areas of physics, 2 different aspects of dynamics in physics, are in fact just different realizations of the same thing. And this is the prototypical example of the unification of forces. And to some extent, the history of physics is the history of unification. So in the modern theories of particle physics, we have learned that the electromagnetic force that I have described here is in fact unified with one of the nuclear forces, and that the electric force and the weak nuclear force are in fact different manifestations of a single, more fundamental object. And likewise, it is conjectured, although certainly it's not known if it's true, that all of the other nuclear forces, the strong nuclear forces, and the electric and the weak forces should be unified together into one more fundamental force. Okay. This is an idea in physics that is known as grand unification. And it is a very appealing idea that may or may not be correct. But what I would like to now describe at the end of class today and moving in to the rest of this week is a slightly more different type of unification. And a sort of unification where we understand that gravity and the classic gravitational force is really unified with special relativity in the sense that the force of gravity, which is something that a priori has nothing to do with special relativity, can really be regarded not as due to some gravitational field or some gravitational potential, but really can be viewed as due to a property of space-time itself. So that is an idea that I'm going to explore, at least cursorily, over the next week or so. But before I do so, let me pause and see if there are any questions. No questions? I should maybe mention, just as a bit of an aside, that you probably will not see again this discussion of the unification of electricity and magnetism until you take a course on electromagnetic waves, which might be a year or two from now. But when you do so, you'll discover that there is a formulation of electromagnetism which treats the electric and magnetic field on completely equal footing and makes completely transparent the fact that they are related in this very fundamental way. So what I'd now like to do is move on to the discussion of general relativity. At the very beginning of this course, I warned you all that one of the goals of this course is not to dive in too much detail into any one particular area of physics, but rather to give you a general overview of many different areas of modern physics. And so, whereas we've been able to go into a rather deep and precise investigation of the formulation and the laws of special relativity, for the remainder of this course, we're going to have to, by necessity, be a little bit more cursory and neglect some of the more involved and mathematical aspects of those theories that we'll be discussing. Okay. So from now on in this course, I'm not going to be able to develop every single aspect of what we're studying from the ground up, but rather I'm going to have to ask you to take a few things on faith, or if not on faith, you'll have to believe me, because I'm a very trustworthy guy. So, what is general relativity? General relativity is the classical theory of gravity which unifies special relativity with Newtonian gravity. Now, we have seen a great deal about special relativity in this course, and so let me just remind you of a few features of Newtonian's theory of gravity. So, Newtonian gravity is really a theory that consists of two different statements about how the gravitational field makes objects move. So the first part of Newton's theory is a statement about how an object with mass will create a gravitational potential or a gravitational field around it. So the gravitational field is usually described in terms of a function phi, which is the gravitational potential of the field. And if we have, say, for example, a point mass m, then the gravitational potential is equal to minus gm divided by r, where r is your distance from the point mass. Or, more generally, if we have some mass distribution, where mass is distributed according to some density, rho of x, where rho of x is the density of mass at a given point, then the gravitational potential is found by solving Laplace's equation, which says that the Laplacian of phi is 4 pi times Newton's constant times the mass density. Now, I assume that you guys have all seen that first formula that phi is minus gm over r. And just for my information, have you guys all seen that second formula as well? Yes or no? No. Okay. Have you guys all seen the analogous formula for electromagnetism, where the Laplacian of the electric potential is equal to the charge density? Raise your hand if you've seen it. If you've seen it. Okay, you haven't really seen it. Okay. So this is not something that is particularly important in this class. So if you haven't seen that, don't worry about it. It's just the second-order differential equation that allows you to determine the gravitational potential around some object given its mass distribution. But for the purposes of this course, the only formula that one really needs to know is this one here. Is this a formula that everyone is familiar with? Raise your hand if you're familiar with this formula. Okay, good. So the first part of Newton's law of gravity was a rule that told you, given some distribution of masses, so if I have a mass here and a mass there and a mass over there, what is the corresponding gravitational potential? And the second part of the Newtonian formulation of gravity is a rule which tells you how objects move in a given gravitational field. So in particular, the motion of objects in a gravitational potential, phi, is given by a force law which says that the gravitational force on an object is minus the mass of the object times the gradient of the gravitational potential. And that, according to Newton's law, is equal to the mass times the acceleration of the object. So, for example, if phi is equal to 0, so that there is no gravitational force, then that implies that A is equal to 0, and the object moves on a straight line. A second, slightly more sophisticated example would be if we have an object of mass capital M sitting at r equals to 0, then the gravitational potential is mg divided by r, so that the force felt by our object is little m times big M g over r, where here little m is the mass of the object being studied. So I should say the mass of the object subject to the force. And big M is the mass of the object creating the force. R squared, thank you. And of course, if I want to use vector notation, I would say F vector is equal to that guy times the the unit vector in the R direction, R hat. But if I just want to use the non-vector notation, I would just say it's M, little m, big M times G over R squared. And the statement of general relativity is basically the following. It is the statement that gravity is not due to a field phi, but rather to a property of space-time itself. So, in particular, whereas the basic object that describes the gravitational force in Newtonian gravity is the gravitational potential phi, in general relativity, phi is replaced by something called a metric of space-time. And this metric is some sort of geometric object which tells you how space-time is curved. So, the mathematics of curved geometries is very complicated. It's a field of mathematics known as differential geometry, certainly one that we're not going to study in this course. But what we will understand are at least a few of the basic reasons why gravity has a geometric formulation in general relativity. And we'll be able to use the basic principle of general relativity, known as the equivalence principle, to understand several of the experimental outcomes and important features of general relativity. Okay, so I'll see you guys on Wednesday. Just an announcement, I have problem set 3 solutions here for you to pick up, which I didn't hand out last time. Problem sets 1 to 3 are graded, so if you haven't picked them up yet, I have them here. Problem set 5 is due Wednesday, and I have also problem set, the midterm practice sheet for you guys to pick up if you like. Okay, hang on. Okay.